Okay, hello everybody. Welcome to this seminar session of our Thursdays at BrIAS. So today we have two very interesting talks, and I'm very happy to introduce the first one. Our first speaker is Professor Andrea Roli from the University of Bologna. So Andrea is someone who's very well known here in various departments at ULB, as he's often visiting us. He has also visited us as a fellow of the BrIAS multiple times. We're very happy to have him here. So actually this is his second talk this year, and we are actually also expecting a third one because Andrea, beside being an excellent scientist who works on swarm robotics and stuff around it, is also a musician, and he promised us also to give us a seminar and maybe a little concert in the future. So I'm just saying this to seal the deal in front of the cameras. And so you are all witness. We will also want to listen to him playing his tiorba or his Baroque guitar. We will see what. So we leave you the choice of the instrument at least. This said, without further ado, I am pleased to leave him the stage, so that's yours.
Thanks, Emanuele, for this nice and bizarre introduction, because now I cannot avoid to plan another talk on that subject. But for today, thanks for being here, and the subject of today's talk will be, let's say, slightly more scientific than Baroque music and complex systems. When I thought about the subject of this talk, I considered that the audience comes from different backgrounds, and I realized that there is a fil rouge in my research since I think about 30 years, that is dynamical criticality. In several parts of the activities of research I've done, I've focused on dynamical properties of the systems from the perspective of a computer scientist. So when computation can be translated into the dynamics of a system. And in particular, there are complex systems that exhibit properties that are very useful for computation. The personal motivation for this subject comes from two books that I read actually when I was still a student. The Origins of Order by Stuart Kauffman, a book I think fundamental for self-organization and evolution in living systems in nature, but also with models that can be studied and applied in computer science. And the book by Roberto Serra and Gianni Zanarini, Complex Systems and Cognitive Processes, that connects beautifully the properties of dynamical systems with the ones of computational systems. These books are from early 90s, but I think they are still now important to describe these subjects. So briefly, the outline of what I'm going to talk about is that we often observe that some complex systems in nature, and so natural or artificial, exhibit some properties, and they are typically poised, so living at the edge between order and disorder. And these systems have this particular dynamical regime that makes it possible for them to achieve an optimal trade-off between flexibility and robustness. And this is something that we very often aim at in designing artificial systems, but also it's a property that we observe in natural living systems. And in this, criticality may play the role of a general principle that can be used both to study and to design systems. I will start with a little bit of background, rather informally. So I apologize in advance for the physicists here, expert in statistical physics. I will be really informal in this introduction. The term criticality has its roots in the theory of phase transitions. We are all familiar with the phenomena of phase transitions in nature, for example, a transition of water from liquid to gas operated by tuning a specific control parameter, which is the temperature, or other general properties like being ferromagnetic or paramagnetic of iron. And in this case, this change is tuned by changing the temperature. But the point is that in all these situations, we can find a so-called order parameter, which is in the model a parameter that undergoes an abrupt change directly or in one of its derivatives. And this is called phase transition. So the point is that we are interested in the phenomena that are called critical, that corresponds to the critical values of the control parameter that produces this abrupt change in the order parameter. But we are especially interested, or actually I am especially interested in what are often called second order phase transitions, which are the ones in which the system shows different behaviors in the two conditions that are separated by this critical surface. So we do not just observe properties that change, but typical behaviors that change. So the bouquet of behaviors that the system exhibits changes in the two sides of this critical line. And very interesting properties, I would say probably the more interesting properties lie there in the critical separation between these two regimes, these two conditions. I'll briefly give you a couple of examples. The first one is the Ising model, which is rather known, and the second one will take a few minutes more than the explanation of the Ising model. It is the one connected to Boolean networks, which are also will be used also in a later part of my talk. So the Ising model can be simply described as a lattice of cells, atoms, that can have two spins, quantified in plus or minus 1. And the system has a function, a general function that is an energy that is given by the summation of the product of the adjacent cells, of the spins of the adjacent cells. So we can see that if spins are aligned, so they have the same sign, then there is a negative contribution to the energy. And guess we would like to look for the minimum energy conditions of the system. If we simulate the system with a Monte Carlo method, then we can apply a simple probabilistic rule for the flip of the spins using a Boltzmann probability, which depends on the difference in the total energy that a possible flip may introduce in the system, and depends on a control parameter, which is called temperature here. Roughly speaking, if the temperature is low, only, or let's say the most probable flips accepted are the ones that produces a decrease in the global energy, while if the temperature is high, then the system may accept also flips in the spins that do not produce a decrease in the energy, so it may also increase it. And in this system, we have an order parameter, so we look at properties of the magnetization, which is just the average value of the spins. In this rather simple description, we can find interesting properties and a phase transition. That, of course, depends on the parameters k and j of the energy function. But here, to keep things simple, let's consider that we have low temperature, and in that case, spins tend to be aligned. And this alignment tendency spreads across all the system. So we may have almost all the spins at -1 or almost all at 1. While the temperature increases, this property is slightly perturbed, and we have then a phase transition that divides this behavior of let's say, ordered possibilities, either all, almost all, +1 or -1, to the disordered regime in which the temperature is such that basically all the spin flips are accepted, and so we have a constant oscillations of all the spins. We have complete random behavior of the system. But the point is that this transition is abrupt, and the larger the system, or the system goes to infinity, it is possible to prove that there is a discontinuous moment at the very critical value of the parameter of the temperature. So this shows in a simple system that depending on a parameter, there is an abrupt transition between a condition in which the system can be in an ordered situation, either all +1 or -1, and it is also a stable condition. And the second regime is a completely random one. So here, basically, every spin have the same probability of being +1 or -1, and it continuously oscillate. Here you see a plot taken from a picture of a nice book on phase transitions by Ricard Solé, in which these points are plotted by a simulation of the system, and you see this clear behavior. But there is another system very rich in terms of dynamics that exhibit a phase transition between order and disorder, and this is called Boolean networks, which have been introduced by Kaufman 55 years ago, almost 57. I don't know if it was January, February, or June, actually, but the paper was in the first paper was in 69. And they were introduced, and they are discussed also in the book that I mentioned at the beginning of the talk, but they were introduced earlier as a model, a generic model for genetic networks. It is a typical case of a system with discrete states that evolve in time in discrete steps. So it's rather easy to study in theory, then it's much more difficult for simulations if we have large systems. The idea is that we have a graph composed of nodes associated to a Boolean value, which represents the state of the node, and a Boolean function, which is used to update the value of this node. The inputs of the functions come from the values of the node that are connected with an incoming arrow to the incumbent node, the node that we are considering. And this defines somehow the structure of the network, while we have to decide also what is the dynamics of the network. So what are the rules that we can apply to evolve in time the network? Here, and for the rest of the talk, I will consider probably the easiest way for updating this system that consists in apply synchronously the update function of each node. So at the very same moment, we update the values of each node of the network by applying the Boolean function. So we read the values of the inputs and we update the state of the system synchronously and applying all the functions, all the Boolean functions in a deterministic way. So in this case, we have a system composed of, if the network is composed of n nodes, we have 2 to the power of n possible states for the system, so all the possible combinations of a Boolean vector of length n. And in principle, we could study the transitions and the dynamics of the system. Consider that we have one successor per each state, per each system state, because the functions are applied synchronously and are deterministic. And we have a finite number of states. So for small systems, no surprise can come. Okay, we could exhaustively explore the state space and know everything about the dynamics of the system. In fact, we could, for this simple network, this is a really a toy model. We can have 3 nodes, and we have for each node a truth table saying what is the possible value. So for x1, we see what is its future state depending on this truth table, and the same for the other two nodes. But the point that is of interest is that if we run this network starting from an initial state, given the properties of the dynamics, we can subdivide the trajectories in the state space in a transient, so a sequence of nodes ending to, and let's say, landing to an attractor, which might be a fixed point, so the system doesn't move any longer from a specific state or a cycle, and the system just goes on forever, repeatedly on this cycle of states. This, for example, is the complete state space of the network that I've shown you in the picture before. We have two fixed points and a cycle of length 2. No surprise at all. So this model can be used, for example, to try to match properties of real cells. We extract some information about genes, and we can create a model, a specific model of that specific that specific cell in given properties. But what is particular interest for me now is a specific model of Boolean networks that is called random Boolean network. And it's this model that exhibits a phase transition that is of particular interest. Let's consider a random Boolean network of n nodes with exactly k inputs per node. This hypothesis can be relaxed, but take it like this because it's easier to explain it. And for each node, we choose k inputs, so k values for the Boolean functions, k inputs for the Boolean function at random from the other nodes of the network. And then we define the function, the Boolean functions, by completing a truth table like this, putting a 1 with probability 0.5. So basically, we flip a coin, a fair coin, and we assign 0 or 1 depending on the outcome of this coin. And we decide what are the Boolean functions. Now, in this, I would say, probably incomprehensible and we could think meaningless ensemble of nodes with Boolean functions that are chosen at random and connections that are random, some interesting order emerges. So let's suppose that we tune k. We can have the number of inputs per each node, 1, 2, 3, 4, 5, etc. If k is equal to 1, it means that every node has exactly one input, so the Boolean functions simply manipulate one input. We have very few options for that. And in fact, what we have is a very ordered dynamics. Here you see the picture, the graph representing the state space of a random Boolean network of 10 nodes. So we have 1,024 possible states for the system. We see that we have just a couple of fixed points and a very ordered way for reaching the attractors. So funnels that define paths to the fixed point, which are really rather rigid. And in fact, these systems have a very frozen dynamics. So if we perturb a state or a node of the system, then the perturbation dies out quickly, and the system settles down again to the same attractor. So it is also robust. And it might work, for example, as a good system for classifying for specific classes, very few classes. It can absorb, it can take as an input the initial state and then go toward a fixed point representing the class of the system. And if we perturb this, this initial state, the network is very likely to go again to the same attractor. But it's a rather poor dynamics. Now let's try, for example, with values of k equal to 3 or greater than 3. I wonder why I didn't choose 2 now, but but let's hold it. Or probably you are wondering why. And in this case, we have what is called pseudo-chaos, we have a finite system, it cannot be called chaos, but we informally say that we have a chaotic condition in which we have very long cycles. So let's consider Boolean networks of size 100, and 2 to the power of n is for us something that has no limit. Is not possible, of course, to make all the steps of an attractor of more or less this length. So for us, it's something without a conclusion. It's not a system that goes towards a meaningful attractor. And it presents the properties that are typical of deterministic chaos for the ones of you who are familiar with it. If we start with an initial condition and we slightly perturb the initial condition, the two trajectories diverge very quickly, exponentially. So we cannot contain the distance between the two trajectories, and just a slight modification of the initial condition produces enormous differences in the dynamics of the system. And it is also not robust at all. So if we are in an attractor and we perturb it, it's very likely that the system goes to another attractor. So for us, it's nothing that reacts in a robust way to the perturbation of the system. No surprise that for k equal to 2, we have a phase transition, and we have exactly the criticality condition, in which the system exhibits a kind of mixture of properties of order and disorder. We have cycles that are usually quite high in number. They are not very long, so they can be executed and represent categories of the behavior of the network. They are robust, so small perturbation does not affect the steady-state behavior of the network. Some perturbations can make the network jumping from an attractor to another one, so there are transitions that are allowed. And so in this mixture, we have richer dynamics than ordered networks, but much more stable dynamics with respect to the chaotic networks. And it can be proven in theory with statistical physics methods that there is indeed a phase transition, and we have actually two order parameters, two control parameters. We have k, but we have also p, the probability of assigning a 1 into the truth table. And in fact, by tuning k and p, we can decide whether to leave or to generate networks from an ensemble that characterizes ordered networks or chaotic ones with a rather high value of k and a value of p, so the probability of having 1 that is around 0.5. That means we have much more variability and possibilities in the Boolean functions. But there is a separation. This is a line, a critical line that separates the two regimes. And in fact, with very large systems, we can observe these properties. And now you have to be precise. We usually talk about the edge of chaos for these phenomena, so the systems that are poised between order and disorder. And it is common to say disorder, chaos, randomness interchangeably. Actually, there is a difference. Disorder regimes can be random. That means that there is no structure at all in the dynamics of the system. They can be chaotic in the sense of deterministic chaos. And in that case, there is a structure. But unfortunately, we cannot make predictions for these systems because they are they exhibit sensitivity with respect to initial conditions. But still, what is of interest to us is that we have a separation between order and disorder regimes. More about that, especially when we study finite systems or living systems or finite systems, these transitions are not as sharp as we can find in statistical physics model. We have point lines or surfaces of representing the critical values for the parameters. But in real life, we have extended critical situations. So we have a range of values, we have a range of behaviors that are exactly a new condition between order and disorder. And it's also important to observe the fact that while in models we have a sharp transition, so a discontinuity in some function, in the real world we have just sharp changes, but not as abrupt as in discontinuous function. So we can somehow live in a critical extended region and find there a place where the dynamics of interest can take place. There are also some interesting properties of systems living between order and disorder. The first one is that if we perturb a system that is critical, usually transient to go back to an attractor, so to a steady state, are rather long. This can be good or bad depending on what we want to use the system for. But in general, this means that there is a computation involving several parts of the system. So this is also linked to the fact that we have long-range correlations between elements of the system. This means that if we take a random Boolean net that is critical or the Ising model in a critical condition, we can find statistical correlations between elements that are far away. That means that information is spread across the system. And another important property that I just mentioned, because it's a very large subject, is connected to scale-free properties. Scale-free properties are the ones represented by power law functions and they are typical of many phenomena that are associated to criticality. The essence of that is that there is not a particular scale at which we can observe a phenomenon, but the phenomenon extends over all the possible scales of the system. So this means that we cannot do averages, for example. Now, what is the criticality, the importance of criticality? Well, I would say since the early 80s, the idea that critical system can behave in an interesting way and deserve to be studied was already present in the studies in complex systems. And the idea is that a critical system can attain the best balance between robustness and adaptivity. And this is something that we look for in artificial systems, for example. And they can be reliable in responding to the perturbation, to the inputs, while providing a large set of possible answers. So I can have a very stable system that answers always the same answer, that gives only or two answers. Okay, that's it. It is stable, okay, but the repertoire of possibilities of the system is really limited. On the other hand, I can have a system that reacts differently from any input, and this is useless because it doesn't provide information to me. But a system that is able to classify the inputs robustly, but still with wide possibility for discrimination, is really an important property. So we usually look for systems with these properties. And observing that this is possible for critical systems make criticality a good candidate for a design principle. There are indeed two versions of the criticality hypothesis. One is connected to evolution, so the possibility of evolving systems, and it's the reason why it is said that living systems are critical, because they are subject to this kind of evolution, and critical systems, it has been proven, evolve better than ordered or disordered ones. But also a kind of behavioral version of this hypothesis that is connected to the capability of using information, so transformating, storing, and sending information and elaborating information in the system. And there have been results in both the sides that I've just quickly mentioned to go then to the results that are more related to my research. There are now, I think, thousands, hundreds, let's say, of papers showing that cells are critical, but not just cells. The brain is critical. There are very interesting results about that. also experimental. And also swarms, ants or birds, show critical behavior in their swarming. So it seems a property that can be generalized across living systems. But also for artificial systems, it seems that being critical is helpful. There are several examples of artificial neural nets that, when poised at criticality, perform better than the other ones. There are examples in reservoir computing, which is currently a very used technique. And in this case, it has been proven that critical Boolean nets perform better than the others if used as a reservoir. And analogous results were also found in local search for optimization. So in this general topic, in this subject that is really wide, from physics to biology to computer science, I made my personal investigations that I'm not going to detail to you today, but I will go to the last one that has to do with robotics and adaptive robotics, and it is, I think, more connected to the activities of BrIAS. But before that, let me mention three important questions that I had in mind when I basically started these research activities in criticality. And some have already, I would say, a partial answer. Some are still to be investigated more. So the first one is, does it always pay off to be critical? Do you find critical systems wherever, as it was in the 80s when deterministic chaos was found, or scale-free networks? Then everything is a scale-free. Now everything is critical. Well, when there is a question mark, often the answer is it depends, and in fact this is the case. Can robotics take advantage of criticality? This is the subject I will talk about, and then I will conclude with some considerations about the implications of criticality for the evolution of the biosphere and the society and all of us. So in general, from results I have achieved and also some other researchers, we cannot say that it is always good to be critical. There are conditions for which a system has an advantage of being critical. The main reason is that being critical is a cost. We need some redundancy, we need some flexibility, so the system cannot be really minimal, should be large enough. Computation is slightly longer than being completely ordered, and so it is not always the case that it is an advantage. So in general, the task should not be trivial, should not just ask for a couple of answers and that's it. It is usually a dynamic task that induces criticality. There is noise, there is uncertainty, and also if a system has to interact with an environment that is critical itself, then it means that it challenges more the system, and so the reactions should be somehow elaborated with care, and criticality pays off in this case. But this is just to answer the first question. Let's move to the second one, and that has to do with adaptive robots. So the idea is to use systems that can be poised at criticality and compare these systems with order and disorder behaviors, disorder regimes, by using these systems to control robots in an online adaptation context. When I say this, I basically refer to a condition that is in other fields called lifelong learning. So we have a system, in this case a robot, that has to adapt some of its parameters, or some of its structural definitions, in order to improve its performance with respect to a given metric. And this has to happen over the course of its activity. So there are not clear training phases and then phases in which the robot is just making its stuff in the environment, but it has to be able to continuously learning what is better to improve the objective function of its performance metric. And I've, of course, used the Boolean networks to control robots. Of course, is because you clearly understand that I'm a fan of Boolean nets and I work on them, so I've used them. I'm not pretending that it was a choice extremely grounded in many scientific considerations. I like Boolean nets, I know how to use them, and so I made these tests. But there are many other ways to control robots, of course. Here we have a Boolean networks, and we have to couple it to the environment in order to control the robot. So we take values from the sensors that are somehow translated into values, Boolean values, that are used to override the values of some nodes of the network. Let's call them input nodes. The values, the Boolean values of some other nodes are taken and then converted to send signals to the actuators. So basically it's something similar to the use of classical artificial neural nets to control robots. The difference here is that we have a different domain for the values and different dynamics with respect to usual artificial neural nets. And somehow some advantages because it's the level of abstraction is slightly higher, but also some disadvantages because we have to do with Boolean values all the time. So we have to translate values from sensors and translate values to send signals to the actuators. And this is the way we can couple a Boolean net to the robot and let the robot do actions in the world and perceive values from the world through sensors. What we can adapt of a Boolean net? Well, the Boolean functions, the links between the nodes, but you can also change these connections. These are not pre-stated, so we can do basically whatever we want in the coupling and in the structure of the network. There is a difference, though. The first two levels directly change or might change the dynamical regime of the network. If I change the Boolean functions or the connections, then the dynamical regime of the network is very likely to change. If I only change these connections and let the network untouched, I do not perturb the isolated characteristic dynamics of this network. What I just change is its behavior when it is immersed in a system, in an environment. I will show you results across all these, almost all these possibilities, but first I will focus on the last two. So we just keep the network as it is, and we try to adapt the connections, which seems really full, because I take something that I will show you is random Boolean nets of 100 nodes, of 1,000 nodes, random, critical, ordered, or chaotic, and then I just try to couple it to sensors and actuators, hoping that its dynamics will let the robot do what I want. I was surprised to observe results, but I don't think it's really silly, because actually what we are doing is that one. We have basically we have a dynamical system that could be rich in its dynamics, and we try to find the proper interactions with the system such that its dynamics has the properties that we are aiming at. So we are not touching directly the system, but we try to perturb it and read its reactions and reinterpret its reactions in such a way that the system behaves or exploits some of its dynamics in the direction that we want to go. So a simple idea is that we can, for example, change the connections from sensors to actuators, to the nodes of the network, leaving the nodes controlling the actuators fixed. So we have already a limitation, and now we limit further the possibilities. We just try to connect sensors to nodes of the network. And let's do things really simple. What is the mechanism for adapting? Well, the easiest mechanism that was introduced in cybernetics: try a configuration, evaluate it, modify slightly this configuration, evaluate it. If the modification is better or equal, keep it. Otherwise, throw it away and try another configuration from the initial one. A classical trial and test. We have no heuristics here to use, or, well, actually, in general, I suppose we don't have them. So I've chosen the easiest mechanism for adapting and the most limited way for coupling the environment to the network. The first test was a simple task. We wanted the robot be able to walk or to move as fast as possible in the arena, staying away from the obstacles. And of course, the goal was to test what is the performance among the different regimes of the network. So we have taken networks from the ordered regime. Given the similarity of this, the symmetry of this curve, we had to take different values for that, but always in the order. Chaotic is in the center, only one is enough, and critical on the two extremes of the line. And we tested networks with 100 and 1,000 nodes. The results, I give you only the summary. Of course, details are in the papers, or I can answer if you have specific questions. Surprisingly, I would say it was not that difficult to find networks enabling the robot to perform properly the task. The best ones were critical, and especially the larger networks, so 1,000 nodes, which is a blob of dynamics, was actually clearly better than ordered and chaotic ones. And this is just a comment, but it's really interesting. The worst ones were the ordered networks. Too frozen, too stiff, no way to move them. Chaotic networks were not performing as good as critical ones, but still not really bad. And this may be a suggestion. If I have a chaotic system, maybe I just need to add constraints to it in such a way it performs rather well or enough for our purposes. And it is better to start from a variety of behaviors with respect to starting from something that cannot provide itself behaviors. But of course, the best ones are critical, that are a mixture of these dynamics. But of course, collision avoidance with controlling only the links from sensors to nodes of the network are not enough. So with collaborators, we made experiments involving also other two tasks, so collision, but also area avoidance. So the robot should also detect the color of the floor and choose the proper one in which they have to stay, and moving objects from a side to another one, avoiding obstacles. And we tested different ways, different mechanisms for adapting the networks. So we can change both the connections from sensors to nodes and from nodes to actuators. We can change the Boolean functions only, so just touch leave untouched the connections, but change the very dynamic of the network by perturbing the Boolean functions, or combine these two. Just a summary of results. overall critical networks were always performing better than the other ones. Here in this case you see that chaotic do not perform well, do not perform as good as in the previous example. Here we have ordered networks that perform that are ranked second. But there are some notable outcomes. The first one is that the best results were achieved by using the mechanism of changing the connections between sensors and network and actuators, plus a little bit of changing the Boolean functions. If we add the fact that Boolean functions can be changed, we can observe that the criticality of the network, if taken as an isolated system, is somehow increased. So if we start from an ordered or a chaotic network and we change the Boolean functions during the adaptive process, these two seems to go or to tend towards a critical regime. So it means that also the adaptive process, reminding very loosely an artificial evolution context, are driving the network towards criticality, because the task is not easy. There is noise in the sensors and in the actuators, so there are elements favoring the arising of criticality. And also these results were confirmed by overimposing noise on the very dynamic of the network. So we perturbed randomly the values of the nodes of the network, not just sensors and actuators, but noise in the controller. And here, criticality was even better than in the other cases. So why this should work? The intuition is that critical systems provide a richer repertoire of dynamics with respect to the other two. And my view is that in this way, by changing the connections of the systems with the environment, we are basically shaping its dynamics. Like sculptures, we have there the material, the matter, and by adapting the connections, we are shaping this material in such a way that the shape is what we aim at. We actually shape the landscape of attractors of this of the system by exploiting the attractors that it naturally provides. So we have available already a very large set of possibilities, and we just have to find a way to couple this with the environment. And of course, this is another piece of evidence that in evolutionary or adaptive contexts, when the task requires it, the system is somehow biased towards criticality. There's a lot of work to do in the future, especially by testing more complex adaptive processes, because we want to have robust and adaptive robots, not just examples in simulations. And also, we are not forced to use always Boolean nets with pros and cons, but we can try other controllers, provided that we can assess their dynamical regime, so we can say whether they are critical or not. Now let's go to the conclusion and the final considerations about the implications of criticality that go to beyond the experiments in robotics. What we have observed is that if we have systems that have repeated interactions and they can change something of themselves, so if we have adaptive or systems in an evolutionary context, when they interact, they usually tend to go towards criticality. So it is very likely that if we apply some analysis technique of dynamical regimes to any level of the biosphere, we find critical conditions. And so we have to think about the biosphere as a nested hierarchy of critical systems, from cells to ecosystems. And the same holds for the society, which is a living system not produced by simply by natural laws, but also by conventions and norms that we humans introduce. So we have a big responsibility here, because we are not doing with rigid systems that are there unperturbed. Luckily, they are not chaotic and completely disordered, otherwise we wouldn't be able to do anything. But they are critical. So we have to be responsible in our actions, in our act, because there are some consequences. First of all, there are long-range interactions. If I touch a system in an ecosystem here, it can have an effect on in time, maybe in long time, but an effect to another system. It is nothing to do with the butterfly effect. It is really a stable influence between elements that are distant in the system. If we apply a perturbation, we do not expect a reaction immediately, as in disorder or chaotic systems. The reaction might happen lately. And so if we act in the society or in the ecosystem, we don't have to expect immediately an answer or a reaction. Sometimes, after a perturbation, if the system is critical, then after a transient, it goes to another attractor, different from the initial one, but not that different. So there might be mild differences in the new steady-state conditions. And this can be a good way to analyze the reaction of the system, or a good way for slightly changing the dynamics of the system. And the other point, I go to the last one. If we want to move a system from its conditions, maybe it is too rigid or too chaotic, and we might try to inject some criticality in it in such a way that we can move it and adapt or condition its dynamics. But on the other hand, we have to be aware of the fact that we live in a critical world. And so the actions that we take have an effect, a long-term effect, on other parts of the systems and on other levels of the system. And I think this is especially important for the ones who work in technology, robotics, but also has to do with the environment. Just an example of application of criticality in soil restoration. Have a look at the TED talk given by Stuart Kaufman. At the end of the talk, he mentions a case in which, by using fungal bacteria's community evolved naturally in compost, it is possible to restore the parts of the environment. So I leave you this. And I have to thank many people for the research that I've done so far, and also the results that I presented to you. Here, some in a given order. But also, I'd like to thank all the people at BrIAS, and also I'm really happy and grateful for this opportunity of the stay. And I hope to see you in the future. I'm going to leave on Sunday, so I hope there will be other occasions in the future to meet. Thank you very much for your attention.
So, thank you, Andrea. So, any question? Yeah.
Hi, thank you. Very interesting. So, this the connection of the sensors how expensive does this look like? Do you try every note?
Good question, very good question. In simulation, we can do everything, okay. When we tried other systems that are, let's say, that can be easily physically realized, we had to rely on some combinations for that, because otherwise it is expensive, yes. And so that's why the results I've presented, the initial ones were just on sensors to show the principle of the experiments, but actually we have to consider both the connections in the two cases, which extend the space that can be searched, and also the Boolean functions or the parameters of the system, which are much easier to be changed. But in fact, this is a technological limitation that for the moment might prevent obtaining complex behaviors. Yes.
Do you think criticality, so nowadays entropy is used as a regularizer often in artificial neural networks or reinforcement learning. Do you think criticality would be a better regularizer? Because I guess a critical system has a high entropy, but not the highest. And now we are aiming for the highest entropy, but maybe we should be aiming for criticality.
It depends on the goals. I think the point is that if you want to maximize the possibilities, then you look for maximal entropy in that. And criticality is a kind of balanced metric for the number of options that you can choose and the robustness of these options. We also try to evolve classifiers based on Boolean nets by letting the system decide how many classes to use. Okay, so the system was free to decide a class is an attractor, so it's easy to do that. But also what is important is that each attractor has a large enough basin of attraction. Otherwise, when you start from a condition, just a tiny change might end up in a different class. So in that respect, I think criticality can be useful if you don't have a given number of classes, but you still want reliable answers from the system that is subject to noise. I'm not aware of specific studies on that. So I cannot give you references on that. It might be, but it depends on the goals.
Other questions? There is a question there.
Hello, Andrea.
Hello.
Hello, everyone. It's Thomas Velos here from the Centre Leo Apostel Research Center that I don't know if you know it, but it has been around for a while. It's an interdisciplinary center at the VUB. And I'm sorry that there was a strike today, so some people could not come. I just got some messages. Yeah, I bike, so yeah. I want to give a small reflection and then a question. Because you end up saying about the responsibility that we have to acknowledge the features of criticality on our behavior, on our actions, especially working with robots, AI, all these, societal issues. But I want to look at the other way around, because if we are also part of these criticality processes, we have to acknowledge we are being influenced by many levels. So that gives another dimension of self-reflection of who we are. Not just what's our impact in the world, but also what are we made of. Maybe we are very ignorant of what are we made of. We might be part of very long transients, and our existence is part of that. So it's a sort of philosophical reflection that maybe contributes to that. And the second question is on the when you were saying what can we change, and we have this system made of perceptor, controller, and actuator. We can change the goal as well. So the goal is left out of the picture, and I think that this is, and I'm open to discuss the fact that this might be a fundamental drawback of the architecture itself to describe systems, thinking on robots and agents in the future, because biological entities have somehow these goals somehow embedded in the architecture. So we can only change nodes so far here to arrive to a goal or perform, but we cannot like modify the goal by the very architecture that is perceptor, controller, effector, which is coming from Rosen earlier than Kaufman. So I wonder if you have gone through this, like questioning the very goal configuration process within the architecture. Yeah, because there's probably criticality aspects for it as well.
Yeah, thanks for the comment and the question. You're right, but concerning the first observation, you are right, and this is and criticality is also a good way to know better ourselves. And concerning the question, we have made experiments with non-specific tasks. So going back to cybernetics, we want a system that survives. So the modeling from cybernetics and Ashby is that I don't care about the goals, your specific goals or task-oriented goals, but you just have to survive. So do what you can for surviving. And we made tests, but these robots are already artificial and they are simulated, but we did this with artificial agents, so even more simplified environments, in which basically the goal of the agent was to keep some essence variable in given ranges. So no goal was specified, and the interactions with the environment were abstract. So we didn't give meanings. Here we have proximity sensors, ground sensors in the examples I've mentioned, and the results I've shown you. But in this case, in this study, it was just an interaction with a Boolean, critical Boolean word environment. And I have to admit, we were looking for criticality there, and there are mild signals that that critical systems work better, but they are not as strong as we expected. But still, with some interesting results. We have a paper published recently in Sensors about that. So you're right. Whenever we add explicitly a task function, it's something that we impose to the system, and it is somehow a simplification of the overall architecture of a model for a living system. Yes.
Okay, so there is a last question.
Okay, thank you. That's an honorable place for a question. Thank you, Andrea. I admire your didactic as well as your research capabilities. Fantastic. So it's a question more of a promotion. You probably know that the work of Gregory Chaitin, who, again, by argument of entropy, but algorithmic complexity rather than entropy, finds. Should they repeat everything? Okay, sorry. So it's amazing that these two are resonating so close by the work of Gregory Chaitin, another great man like Kaufman, who proposes that Darwinian evolution, is neither random nor ordered, but it has to be critical. And he has written a very small book, but very strong argument, proving Darwin, where he states, coming from a different direction, that of algorithmic complexity, he arrives at the same things like you.
I answer quickly because this would require a long discussion. But yeah, I'm aware of that work, and I like also the perspective from algorithms. in that sense. So very often chitin is just cited for the maximum complexity of a program and not for this part. Yeah. As you know, and several people here, I'm really influenced by the work by Kaufman, and so I cited him and his work. But there are other, of course, other who say maybe the same thing or a similar, reach a similar conclusion from different perspectives. Thank you.
Okay, so at this time we have to interrupt here for the questions, so I invite you to continue to speak with Andrea during the well-deserved coffee break that we need before going to the next speaker. So as you know, we always have 2 speakers in this Thursday, so I propose you a small coffee break, and then when you will hear a noise, come back here. Okay, so welcome back, everybody, with the second speaker of today, that is Professor Luca Magri from the Imperial College of London. So, as a first thing, let me say that we have decided to torture Luca. So, he has a fixed podium, a fixed microphone, while we know that he likes to walk around and be free to move on the stage. Unfortunately, he cannot. So this is, of course, another experience of torturing one of our speakers. Today we are in the mood, so it's fine, I think.
Glad to participate.
So it's really a pleasure for me to introduce him. He's doing several very interesting work for what concern putting together what is machine learning on one side and what is not throwing away some hundreds of years of knowledge of physics. So trying to merge these two words together, or at least this is what I understood, but probably we will understand something more with this talk. So I leave you the stage.
Well, thank you very much, Emanuele, for the introduction. And yes, I move a lot and I also shout a lot, so probably I should just stay away from the microphone. Yeah, so I'm gonna present, we don't have so much time actually, so I will try to squeeze everything in 40 minutes, 45, so I had to cut down actually part of the presentation. The original title was Scientific Machine Learning for Chaotic Forecasting, and it's a bit, now not clear if I'm gonna talk about real-time digital twinning. And probably I'm not gonna talk about it, but hopefully the chaotic part will be as interesting. So you can see two pictures here, and that's exactly the summary of what Emanuele said. I try to combine physical knowledge, pictorially represented by the blackboard, equations, symmetries, anything that we are sure about, let's say, and also data that comes from the movie Matrix, if you are familiar with it, and which is, of course, concerning more machine learning and other techniques. So this talk is fairly pedagogical. I'm actually happy that Andrea already gave a talk on chaos, but to some extent I'm going to take a step back because I'm going to explain some more fundamental things and then jump to the applications. So this is a pedagogical seminar meant for a very broad audience. I know that not everybody comes from my area, and also within the audience there are different areas, so it's not an easy job to do. So I'll try to put everybody on the same page for the first 20 minutes. The slides are clearly high, medium level, so we're going to see just, the tip of the iceberg. And I'm not going to be as rigorous as I hope I am actually in the papers. But if you do want more rigor, if you do want more explanation, please feel free either to interrupt me. That would be great, to engage a little bit. Just raise your hand while I talk. Or, of course, speak to me, email me, or just read the papers. Okay? So this is the ambitious outline. So first of all, I'm going to talk to you about something that certainly you know already, but I want to give my angle about that, which is how to model complicated systems, okay? Second thing, I'm going to talk about chaos, and explain what are the challenges in predicting the evolution of chaotic systems, both from a scientific and a machine learning point of view. And then I'm going to talk about how we predicted turbulent systems, which are chaotic systems, and of course, quoting predicting, and you will see why I'm quoting the word predicting. And I'm going to give you another example of how we can merge physics and machine learning to optimize very complex systems such as wind farms. If there is time, I will talk about the real-time digital twinning, but we'll see that later. Right, so this is the first slide that I usually present, just to give a picture of what most scientists, I believe, and also myself do. So we aim usually at modeling, systems that are complex and nonlinear, in my case, chaotic even. And we are happy about our models when our models get the right answer. I think it's obvious, right? So we want our models to be predictive, but it's not enough, clearly. We want our models to be predictive for a variety of different initial conditions or boundary conditions and parameters. So we want our models to be robust. And in my specific case, I also want the model to be as simple as possible, okay? So if you do high fidelity simulations of turbulent systems, you need probably hundreds of millions, if not billions, degrees of freedom to solve the equations of motion. So I call that as a very high fidelity and predictive model, but not simple. Simple because it's huge. In my research, I tried to have simple models, so smaller models, reduced order models that are inevitably less predictive, but they are quicker to run. And also, in ideal, we want this to be in real time, so every time we observe the system, the model can adapt quickly and become more predictive. Now, these 4 requirements, in particular the first 3, are clearly difficult to achieve simultaneously. Either you achieve predictive capability, and to do so, you usually need a lot of degrees of freedom to model all the details of the system, or usually you achieve simplicity, so a reduced order model that is quick to run, computationally cheap, but it is not as predictive as high dimensional models. So the idea is to combine the scientific knowledge we have about the system in terms of physics and other prior knowledge and the power of machine learning to close, if you like, the models. So let's state something very obvious, but it gives the picture. So as modelers here, there is little control, by the way. There's no robotics at all, and there's going to be more about modeling, dynamical systems, artificial intelligence for science. So in modeling, in general, we want to come up with something like that. Okay, your Q could be pressure, could be velocity, could be electromagnetic field, could be anything you like. It's your state. Okay, so what we want to do is actually predict the future of a complex system. And to predict the future, we have a cause, which is on the right-hand side, Q is your cause. And then you want to predict the effect, okay, that is basically evolving the system. And you want to predict basically Q dot. And typically, you have a model F, for example, partial differential equations and so on, that require boundary conditions or initial conditions to be solved, okay? Now, if you have F and you're happy with it and you have numerical schemes, you can integrate and you get the solution. Game over, okay? So now, how you integrate, it takes decades, actually, to find numerical schemes that are very stable, like in CFD, computational fluid mechanics. But in principle, if you trust your F, then, you know, formally and even numerically, you can integrate and you're done. The interesting thing is when you either do not have F at all, okay, which is, you know, really you don't have knowledge on the system, or maybe F is extremely expensive to integrate, so you cannot integrate it, or integrating it will take an extreme amount of time. So the other paradigm of trying to understand how systems evolve is to look at the data, clearly, okay? That's the extreme end of the spectrum. We are giving up on the knowledge of F, and we're trying just to look at D, our data set, and therefore try to learn from how Q is going to behave in the future. Now, the data we deal with usually are sparse, so we don't have access to all the components of Q. Typically, they're discrete. They come in different times and not in continuous way, and certainly they are noisy. So usually when we learn from data from an equality, we move to an approximation symbol, okay, which is actually essential philosophically and scientifically. So the two paradigms, this is a spectrum, is a big spectrum. There is, at one end, the data-driven spectrum, also known as machine learning, if you like, or empirical methods. So that's a great method because from data you learn correlations, interpolations. It is fantastic because it's adaptive. And by adaptive, what I mean is that every time you have new data or new data sets with better quality or new knowledge with new data sets, you can just, you know, embed and, you know, feed your machine learning method with new data for it to become more predictive. That's what I mean by adaptive, okay? The problem is that, of course, these data-driven methods are, physics blind. They don't have constraints, which is a good thing for computer science. It's not, in my opinion, a good thing for science. So take the example of a neural network, okay? A neural network is, you know, a universal approximator, all these nice things. What does it mean practically? It means that, you know, there are an infinite possible solutions and options of solutions that a neural network can find, okay? So this is the space where the neural network is gonna look for solutions. The space is infinite dimensional, okay? And it's dark. It's dark because the neural network, the only thing that it knows is, of course, the data you give the neural network and the initial guess. Of course, there is an algorithm then to converge it, but those are the very little things the neural network starts with. So if you want to see the neural network as a flashlight, this is the initial condition, okay? And the movement of the flashlight is the gradient-based optimization scheme. And you have an infinite amount of degrees of freedom you can explore, and because you give an initial condition, and because you have a gradient, and because there exists very likely a local minimum around, because the landscape is very non-convex, you're going to converge towards a portion of the solution space. So this is fantastic, and that's why it's very successful in computer science, because it's extremely flexible. You know, you don't need to know anything about your system technically. With the right initial guess and the right, luck, you can end up in a nice area of the data space. On the other extreme end of the spectrum, there is the physical modeling. Okay, physical modeling means coming up, with equations. It is fantastic because it's causal, so you have a Q dot, which is exactly the causality we look for. It's fantastic because it extrapolates. You look at, an apple falling off the tree. You adapt some genius level kind of brain like Newton, and then you can extrapolate that law to the planets, okay, until, of course, higher order effects come in for general relativity. So the third thing is that physical knowledge comes from equations, which is good. But the bad things of physical models is that they are very rigid. And by rigid, what I mean is that you need to identify the principle, you need to translate the principle into mathematics, you need to find numerical scheme to solve the equations, and you need to find an HPC platform to probably solve your equations. And if the final prediction doesn't match the experiment, then there are many places where you can change your scientific workflow to make things work. So if you think about the flashlight, in the infinite amount of possibilities, an equation is constraining where to look at, okay? That's exactly what is an equation, a physical equation is about. So a flashlight can only basically observe a portion of this infinite solution space, okay? And that's the rigidity I'm talking about. That you cannot see anything else other than what the equation tells you. So if the equation is perfect, you don't need to worry. If the equation is not perfect, you do have a problem. So what we do is not necessarily 50-50%, but what we do is to combine the strength of the two systems, the flexibilities, rather than systems, I should say approaches, the flexibility of data-driven methods and the constraint that Mother Nature basically imposes into possible solutions to the problem. And that's what scientific machine learning is about also, is to combine the two things. So if you want to see the flashlight, we start in a place that is constrained by physical knowledge, and that constrains all the possibilities, and then we still leave the flexibility to explore some unknown terms given by the neural networks or other machine learning tools. Okay, well, this gives you a little bit of what scientific machine learning is as far as this talk is concerned. If you have any questions, just raise your hand, please do. Because now I'm going to talk about the systems we want to be able to predict through scientific machine learning, okay? And the systems we want to be able to predict is chaotic systems in our case. Okay, so if you think about this Q dot f of Q, the first equation there, our f, okay, is something that, when you apply it to Q, and you integrate it, will give you something that is not only non-linear, but is also chaotic in time. So we're going to look at deterministic systems in this part of the talk. So there is no stochasticity in principle, as Andrea was saying before. I mean, they are perfectly predictable in principle, but practically they're not because of the properties of F, okay? So the systems we look at are chaotic, meaning that F will amplify all infinitesimal perturbations applied to the system. Example of chaotic systems that are real meaning realistic and of engineering interest from a fluid dynamics perspectives are these three, for example. These have from the order of tens to billions actually degrees of freedom, so they are quite huge simulations. The first one was done by a former postdoc of mine and also student in ULB, by the way, Anko Adoan. The second is turbulence. I'm not going to explain exactly what you're looking at, but it is basically a fluid mechanics problem in a box, and then you can see basically all the structures, chaotic structures appearing. The equations F that is underlying the problem here is Navier-Stokes, if you're interested. And the third one is a jet, basically, that is not only turbulent, but is also reacting with chemistry. So these are examples of very high-dimensional chaotic systems we are interested in predicting. So let's take a step back and understand chaos from three-dimensional systems, which are those we can visualize easily. The properties of this system and the 1 billion systems we just observed are very similar. So this is, as you might know, the Lorentz system. It's quite a prototypical chaotic system. So you see two colors. One is blue, one is yellow. And the difference of two colors at the very beginning when I played the video was very small, okay, on the initial condition. If you just integrate the same equations, okay, with either very small difference in initial conditions or maybe you run the same initial condition but on another computer, so there are different floating point errors, you will at some point end up in having two completely different solutions. Okay, you see that the two patterns diverge, okay, at some point, and that is basically what makes a system chaotic, okay? The divergence basically of infinitesimal perturbations. At some point that's going to happen, maybe sooner if the perturbation is big, and later if the perturbation is smaller, but it's gonna happen, okay? So what do we mean by predicting chaotic systems? So take basically a time series. This is just drawn by hand, so it's probably not even realistic, but just to give you an idea. So suppose this is a chaotic time series. It's some observable, and time is the horizontal axis. We just basically said that we cannot predict, you know, the evolution in time of the time series because of the very nature of the dynamical system, okay? So, but the question is what can we predict, and what do we mean by predicting chaos, okay? There are some quantities in chaotic systems that are completely predictable, okay? One of the quantities of interest, it's not the only one, is the PDF of the signal. If you take your time series, you know, and you bin it in small bins, you can construct an approximation of the PDF, and that is actually something that in principle you can predict because it doesn't really depend on initial conditions, okay? Implicitly, we're assuming to work with ergodic systems, clearly, but it's a fairly acceptable assumption in most cases. So what is basically one of the things that we can predict in chaotic systems? We can't predict the time trace or series, but we can predict something that is more global. And, oh, I don't have the cursor here. So one thing we can predict is this coefficient here, lambda, is called Lyapunov exponent. And to some extent, in my field, you can characterize and you can say that the system is chaotic if that exponent exists and it's greater than 0, okay? So you see that for any initial condition, okay, this is something you can prove, but just believe me, okay? For any initial condition, you will have that the amplification of initial condition or the error in initial condition will grow exponentially with a growth rate given by this lambda. And this lambda is a property of the dynamical system, you know? It depends on your f of q, right? This is something you need to take as given. And that lambda can be predicted, actually, and it is actually a great measure also about how good your predictions are in chaos. What is that lambda practically? So if you take the initial conditions I was talking to you about, the blue and the orange, and you plot in the left panel, you know, the log error, the log norm of the difference between the two conditions and the evolution of the same, you will have a seemingly linear region always in your system. And when you have that linear region, it means that your system is deterministic and is chaotic, okay? And the slope of that region is exactly the Lyapunov exponent. So if you have a steeper slope, the Lyapunov exponent is bigger. Smaller slope, the Lyapunov exponent is smaller. If the Lyapunov exponent is 0, you will not have chaos. You will have probably a periodic solution or something more regular. Right, so you can calculate Lyapunov exponents. These are, for example, two cases. These are big cases. It's very easy to calculate Lyapunov exponent for a Lorentz system. You can do it on your laptop in a matter of really a few minutes, if you like. It's less easy to do so for large dimensional systems, but we did so, and just to give you some flavor and understand the Lyapunov exponent, we apply these ideas. There is no machine learning so far. This is just an idea of how we can basically assess whether we capture all the dynamics in a large dynamical system, in this case being a jet. And just look at the blue curves on the right-hand side. Disregard the reds, please, for now. So different curves, different blue curves, have different resolutions. So for example, the dashed curve as a mesh, okay, as basically a grid where we calculate our CFD computation that is very coarse, so it doesn't capture all the dynamics, whereas the solid and thick line, blue line, has a very fine grid where we can, safely say that we are capturing all the dynamics that is present in our dynamical system f of q, where f is Navier-Stokes here. Okay, so the Lyapunov exponent is the slope of these curves, as you can see, and one metric to basically say, okay, I am simulating correctly, I'm capturing correctly chaotic dynamics in high-dimensional systems is to say I'm capturing correctly the Lyapunov exponent, okay? It is a necessary condition rather than sufficient, but it is a strong condition. So we propose basically using the Lyapunov exponent as such metric. For example, if you look at the thickest blue line and the second thickest blue line, they basically have a very similar slope, meaning that we can use the grid and the resolution from the thinner solid line instead of the thicker, which is, in this case, had a few, I can't remember the exact number, but it was substantially coarser. Okay, so this serves as a guide for numerical simulations, for chaotic systems when you are interested in time-varying dynamics and not just the statistics. So the things that are predictable and the things we measure our machine learning tools and methods are usually Lyapunov exponent, which is one. You can also extend this reasoning. There is also an entire spectrum of exponents, which is also important to capture at least the dominant part. The dimension of the attractor, which is a function, if you like, of the Lyapunov exponents, and the statistics. Statistics are super important. If you don't get the statistics of your signal right, you certainly you're not predicting the signal correctly, okay? So this is what we mean by predicting chaos. We do not mean that we want to predict the time series forever, because if we were able to do that, the system probably wouldn't be chaotic, okay? It's just not possible to do. It's a very important concept to keep in mind. Right, so how do we do that? There are different ways to do that, and I like a lot this way, although we tried a few other ways. I'm going to be quite quick in explaining this, so I just give you a little bit of the picture of how the problem can be treated from a data point of view, and I'm going to explain very high level what kind of machine we are using for that. Okay, there are other options which I'll comment on. So this is our data. Let's say we have a dynamical system with pictorially 4 degrees of freedom in this case. These are our observables, our data. Okay, and we have, of course, this data is ordered in time. This is time series forecasting. So the time is a sort of a ordering index. This is our data set. Okay, and we want basically from the orange, which is now, okay, the present, we want to predict, for example, let's say the next time step as an example, right? So that's the sort of a mission. We want to find a machine that, given the present, it can predict the future. And in this specific example, pedagogical example, we want to predict the next time step. So there are many ways to do that, and gated recurrent neural networks, LSTMs, nowadays transformers, which do that in a different way. But in my opinion, one of the simplest ways that proved to be very powerful in chaotic systems is reservoir computing. And how does it work, reservoir computing? First of all, I'll explain what you're looking at quickly, and then I'll give you a very hand-wavy explanation of it. So the first thing we do, you take the input U, that's your observables, the thing that you actually want to predict, and then you linearly expand it to a higher dimensional space. So you create something fake, artificial if you like, that is higher dimensional, okay? And that will be your reservoir. The reservoir computing term is centered around the concept of reservoir, which is indeed this kind of expansion to a higher dimensional space of your observable. Then you project back with a W out, okay, to your physical space, and you compare your solution, your prediction at the next time step, n+1, with the labeled data set, the reference solution from the data set. You therefore construct an error metric, which depends on some hyperparameters, but I'm not going to go into the details. And the good thing of reservoir computing is you sweep the entire data set, you construct your mean squared error, and the good thing is that this ends up in a quadratic optimization problem, as you can see here, okay? Just if you don't see it, just believe me. It's a quadratic optimization problem, and therefore, if you find the optimum, you have found the global optimum. And you do not need back propagation, because it's a quadratic optimization, so you can get just a solution with linear regression, a linear system resolution. So this has proven in many works to be very good at predicting chaotic systems. There are different things you can use. LSTMs are very popular. The drawback of LSTMs is that they needed back propagation. So the optimization is a non-convex problem, whereas in reservoir computing, it is a convex problem. The drawback of reservoir computing is that you need to expand your observable to a higher dimensional space, and sometimes this expansion is substantial, okay? So if you have a large dynamical system, you would end up in an even larger, larger phase space with more degrees of freedom, and that's a bit of a bottleneck. Also, LSTMs have the same. If you're familiar with them, you have the cell state, the hidden state. They are effectively something that you project out in a higher dimensional space, but reservoir computer, you need more than that, okay? So in general, recurrent neural networks and reservoir computers, they can be applied for dynamical systems that are not huge, okay? So they have, let's say, not billions degrees of freedom, but more on the orders of tens, hundreds, sometimes thousands, but not more, okay? That's the main drawback. And we worked a bit on this area quite a lot, so there are many variants and also many ways to train these things that we proposed, and of course I would be happy to talk offline about that. Okay, so now we have all the tools and we can see some application. I still have to talk about a final idea to see an application, but so far we discussed about chaos as a dynamical system, Q dot equals F of X, F of Q, okay? So turbulence, or in general fluid mechanics, is governed by partial differential equations, Navier-Stokes, for example, if you are familiar with the topic. And well, the problems of partial differential equations that are technically infinite dimensional, okay? Practically, they are big systems, but technically they are infinite dimensional, and therefore you cannot just use the idea of reservoir computing or recurrent neural networks on a state vector that is technically infinite or practically gigantic, because of the same reasons I just talked to you about. You need to expand your vector in something bigger, and you cannot expand a big vector in something even bigger, okay? So we need to think about how to predict turbulence with machine learning with the tools that we have from machine learning. Here, this is where domain knowledge, is useful. I mean, it's always useful, but here it's in particular useful. Because we know something about dynamical systems, and we know something about fluid mechanics, we know that fluid mechanics is a dissipative system, okay? Well, that's quite easy to know. Even if you're not in the field, you just look at the equation and you see that there is some dissipation going on, okay? There is a Laplacian. So, what does it mean? Okay, why is that important to make this observation? It's very important because take a phase space. This is a phase space in three-dimensional, just to visualize it. These are, the phase space is all the possible numbers, that you can think of that comes in triples. Okay. Now, take some initial conditions that are the dots. So. You can take as many as you like, and you can sample the entire phase space in principle, in mathematically what I mean, and then apply your f of q on that, in this case being the Lorentz. So what we know is that when you do that, okay, independently of initial conditions, under the assumption of ergodicity, you will end up always in a portion of this infinite phase space. Okay, this is an incredibly important thing. Okay, the notion of attractor we were talking about with Andrea. So, this is very important because if you think about it, this is telling you that among all the infinite possibilities, there is actually a fairly limited set of values, although it's still huge, but it's more limited than all the possible infinite possibilities a set of values that your solutions can take, okay? So that's number one thing, the notion of attractor, which is in Lorentz system 3 dimensions, and there is the same concept also in Javier's talks in infinite dimensions or very high dimensionals. So not all the dimensions are useful. This is the main point. In 3D, you cannot see that well, but you can convince yourself that if you look at the attractor, you could, intuitively say, well, it looks like more like a 2-dimensional object-ish, okay, embedded in a 3-dimensional space, okay? It's not exactly 2-dimensional, but okay, if you look at this attractor there, it looks like a 2-dimensional object. Now, this means practically that in principle, you could find approximately, say, 2 coordinates to model something that actually initially needs 3, okay? This is not perfectly rigorous, and I'm happy to elaborate later on. Now, the advantage of moving from 3 to 2 is little, so we don't want to make any fuss about that. But the advantage of moving from, turbulence, like millions of degrees of freedom, to something smaller is actually a key for time series forecasting fluid mechanics. So we can use reservoir computers or recurrent neural networks, but we need to have an extra passage for turbulence, okay? Because we need to find this set of coordinates to somehow approximate only the portion of the phase space that we need to find the solution, okay? Right, now I'll tell you a little bit about what we are trying to do from a practical point of view, and I'll tell you also how we're gonna do that. So we took this problem, and it's not important if you are not familiar with fluid mechanics, but we have basically, this is a sort of you have a flow coming from the left, imagine a flow, okay, air coming from the left, and then there is an outlet, so it leaves that domain, that kind of box on the right-hand side. And the top of the bottom are kind of walls. You can think of walls. Okay? The rest is a periodic kind of boundary conditions. Now, the thing that's very important to notice is, first of all, that is an example of turbulence, if you're not familiar with turbulence. So even qualitatively, without defining it, you can see that there is chaos, both in space. That quantity of interest is related to vorticity. And whatever that is, you see that is very irregular. So it's chaotic in space and also in time. If you plot on the right-hand side, the energy, the global energy of the entire box in time, you will see that the time series is very erratic. It's deterministic. It's completely, in principle, predictable, but it's practically, absolutely, seemingly random, but not random. Now, what we want to achieve, we want to find a way to, instead of using, in this case, around, this is not a huge simulation. We used something reasonable, which was 1 million degrees of freedom, okay, from the original simulation. We want to find a low-order model, or I should say a reduced-order model, that basically is able to predict the chaotic behavior of this turbulent flow, both in space and time, okay? Why do we want to do that? Because in the future, we would like to have, something maybe with hundreds of degrees of freedom, to predict the same accuracy that at the state of the art requires millions of degrees of freedom, okay? So to basically speed up the process. The bottleneck of fluid mechanics computations is indeed the complexity, the time that you need to solve the equations. So we want to get basically the time series right, as I explained earlier, and we want to get the PDF, more importantly, right, okay? And not one thing, this is a very challenging problem, because the PDF is not really, it doesn't look like an exponentially decaying PDF. It has a very fat or heavy tail, as you can see, because this problem not only is chaotic in space and time, but it has these peaks here, as you can see, that are technically, from a dynamical system point of view, extreme events. You see one peak there, but if I were to show you a longer time series, you will see more and more, okay? And the PDF, of course, contains the frequency of these peak events, which live in the heavy tail, okay? So they are large, quite far from the standard deviation, but not so infrequent. So the tail is not exponentially decaying. Okay, so we know that this huge system, many degrees of freedom, will, a priori we know that it converges towards an attractor, and we know a priori that that attractor is smaller than the original space. We know that. So the question is, how do we find an approximation of the coordinates of this attractor? Okay, that's the computational question. So I like to think about this system instead of looking at, this is a kind of a fluid mechanics field picture, but I like to think more in a classical mechanics picture of phase spaces, okay? In which in the phase space, your system is always a point, okay? I like to think in points. So the phase space Rn, n is like around 1 million here, is where the turbulent solution is simulated, okay? We know that there exists another space, which I drew as a sort of a potato, okay? It is not as Cartesian and as nice as the original space, but there exists another space that is this manifold where the dynamics evolve in a statistically stationary regime that has less degrees of freedom. We want to find basically this manifold such that when we project our solution from the latent space, as we will call it, from this latent space back to the physical space, okay, we will have basically a quantitative match with a real solution, okay? Real meaning the actual solution. So there are so many questions that can arise now. The first one is, okay, disregard the maths for a moment. The first one is how many coordinates, what is the dimension of this manifold? Well, there are some upper bounds in the theory, okay? You can have an idea on the size of your manifold, and one of them is a Kaplan-York dimension, which is practically difficult to compute for very high dimensional systems, but it gives you some sort of an idea if you have an approximation of it at least. And there are other ways to do that. So coming from physics, we have a way to at least start our search of the manifold coordinates, okay? And second, how do we do this? You know, how do we find these coordinates? So if you look at the problem, this is basically starting from a big vector, the blue one, compressing the vector to something small, which is the potato there, and then projecting back, if you like. It's not really projecting back, it's not a projection, but let's say decompressing, decoding back the vector in the physical space, okay? So this is exactly a sort of an autoencoder if you are into machine learning or if you work with autoencoders. You are trying to find basically the identity, well, an approximation of the identity function in which you have less degrees of freedom in the bottleneck, okay? And that's the latent space. Now, in the simplest form, this is a nonlinear transformation, okay? Z is basically an encoded structure of your initial signal U multiplied by some parameters. And your U tilde is your, basically output of the autoencoder, which will be another function, nonlinear function that decodes the output. Now, this is there is no simpler way I can think of to explain autoencoder because I wanted to keep it high level. So you create a cost function, okay, with respect to the data. In this case, it's a quadratic, it's an L2 norm. You can make things more complicated if you like, and some regularization, and that's your cost function, and you train your autoencoder, okay? And then you find this set of coordinates Z, which is actually what we care about. How do we do that? Well, I can talk about that a lot, but we don't have much time. We use convolutional neural networks, which is a principal choice in this case, because convolutional neural networks are based on filter operations, okay? And the turbulent flow has some local correlations, spatial correlations, and has some structure that is particularly amicable to filtering processes. This is a more domain-specific, again, piece of information that is important to keep in mind. So the autoencoding is done with a convolutional network autoencoder. And once we have found the latent space, then because the latent space is smaller, we can use recurrent neural networks, in our case a reservoir computer, to predict the dynamics. That's the trick. So this is actually the entire idea. I'm going to skip this in the interest of time. I'm going to skip basically all the technical details that usually are those that excite me the most. But anyway, if you have questions, just ask me. So we collected our data, we produced our data with simulations. We did a lot of work to find the right autoencoder, which is not a piece of cake. I mean, unfortunately, there are hyperparameters, as you know, and that requires some thinking. And yeah, what was I saying? Thinking. I was saying thinking. Required thinking. Hyperparameters. Autoencoder. So I found the autoencoder. Okay, and then we encode into the latent space the data, and separately we train a reservoir computer on that data. Okay, validate it, and then we have, if we have done the homework correctly, we have a completely autonomous dynamical system, the reservoir computer, that doesn't need to be trained anymore. It can evolve on its own. It is effectively a Q dot equals F of Q system that can produce the dynamics. And then we decode back the dynamics through the decoder to make sure that it's physical and to gather the physical quantities we are interested in. After we have done all of this, we took months and a lot of work. At the end, you end up with lines in a plot. Okay, this is actually the fruit of many months of work. So what you're seeing is, again, this autoencoder reservoir computer, okay, which is evolving on its own. It's not trained anymore, and we are gathering the statistics, you know, that this solution produced by this machine is producing. One piece of statistics is the statistics is the mean profile, streamwise profile. The dots are the correct solution coming from the numerical simulation. The black is what comes from the machine. In this case, it's very accurate. And then we can also look at higher order statistics, the RMS, and so on. And as you can see, the errors concentrates around where the gradient is biggest, which is where there are the peaks close to the wall. But overall, the statistics are well captured. Of course, when I say statistics here, I mean the first two moments. An interesting thing, I don't know, how many of you are familiar with the PCA? Okay, so a lot of people, good. So if you think about that with PCA or POD, which is the same thing, you know, you can do the same thing, you know, compress and decompress. The only difference is that with the PCA, the compression and decompression is completely linear. You can find a latent space that is a linear subspace. Whereas with autoencoders, as we use them, you find a nonlinear manifold, so more expressive. Well, this is not surprising, but it's always good to keep in mind why we move to nonlinear things instead of linear. If you, in the horizontal axis, you have the number of, horizontal axis is a dimension, sorry, of the latent space. Okay, so the number of coordinates in latent space in the autoencoder, or the number of POD modes that we retained. And on the vertical axis, there is the reconstruction error of the autoencoder. Basically, the bottom line is to have the same reconstruction error, let's say here. Okay, to have this kind of reconstruction error, you need, well, I don't know, let's say around, in this case, if I remember off the top of my head, around 1,000 coordinates in the nonlinear autoencoder, as opposed to around 15,000 for POD modes. It's not surprising. Of course, we need to pay a price. You know, we need to train an autoencoder. But the message is that the nonlinearity gives you a order of magnitude more expressivity, which is absolutely essential. The second thing is that we can see how our autonomous machine is predicting the dynamics. Remember, this is honestly one of the, in my opinion, one of the most challenging cases I can think of to test a time series forecaster, because it's spatio-temporally chaotic and there are extreme events. And it's really complicated. So let's look at the first, the top panels. You have an orange curve. That's the curve coming from the numerical simulation, and the black curve is coming from our machine. And basically, you see a vertical line. So that vertical line is the initial condition we gave to the machine, and then after the vertical line, the machine is evolving autonomously, okay? And we are just basically comparing the solution that comes from integrating Navier-Stokes and what the machine is telling us. And the important point I want to make here, the solution do not match exactly. We know that we don't even want them to match exactly, but the important thing is that we capture exactly the occurrence in time and in amplitude and also in duration of the extreme event, okay? This was quite a good outcome of this work. And how about the statistics? I mean, I talked about first and second order moments. of course, we ran the statistics for longer, okay, and we were able to capture approximately the PDF, as you can see. The orange and the blacks are the two signals, one coming from simulation, one from the machine. And we were able to capture low-order statistics, but also the high-order statistics. Actually, I should have updated this figure because this was one preliminary result. Now we have the fully converged PDF. And basically, the two lines converge also at, in the heavy tail. Good. Well, it's over the time. So real time certainly is gone. Let me just wrap up at least this one. I just wanted to make final comments, which I will just touch upon. How do we know that our machine is physical and is not just some black magic coming from machine learning? Well, we can post-process our machine. Our machine is a perfectly reasonable dynamical system that can be absolutely analyzed with typical dynamical systems tools. I'm not going to explain all you're looking at, but what I'm going to say is just something about the top right figure. Okay, one of the most important quantities to make sure that you got the right representation dynamical system is always spectral properties. Okay, it's an absolutely necessary condition to convince yourself that you have the right dynamical system. So the Lyapunov spectrum is the spectral property basically that characterizes dynamical systems, as we already explained. And we have basically a very good match between the actual spectrum and the machine spectrum. Okay. That means that the machine has learned something that is invariant, okay, which is the spectrum, is the invariant quantity, doesn't depend on the representation, and therefore it's physical. Okay? Yeah, what's under the rug? I mean, this was a real rug. I mean, I didn't talk about, this is my rug, was my rug in somewhere. Hyperparameters, I already touched upon that. Because, of course, everything works marvelously, right? But I want to be honest. The problem is hyperparameters. I mean, all the part of training, which is very obvious for people working machine learning, but it is exactly the main criticism the machine learning has in the physics community, okay? When people try to say, oh, machine learning is curve fitting, you need to tune things, well, it is true. It is a bit true. So there is a lot of research we are doing to try to find hyperparameters by prior knowledge. I gave you some hints today on how to find some hyperparameters prior knowledge. Kaplan and York mentioned these things, but there is a gazillion more that should be researched on. Anyway, just to finish, this is just a promise, last minute, completely different, but just to say, we put together all these ideas. I just wanted to show you a video, to be honest. That's why I'm talking about wind farms. We basically merged physical knowledge and machine learning models in a way that is not in a way that is quite similar to what we discussed, okay? And we optimized a really large dynamical system, which is wind farms. So this is a video that was made by Andrew Moll, and but it represents exactly, Andrew Moll is a PhD student of one of my colleagues, Sylvain Lézé. And in wind farms, one of the things that, this comes from Ixelles, so it's not just ChatGPT, okay? So in wind farms, the thing that you want to control, you have two things you can control, is where you put all the wind turbines, okay, to maximize your power generation, and what is the inclination of the wind turbines. As you can see, all wind turbines, they create this wake, which is huge, and it's also beautifully turbulent and complex. And this wake, of course, affects the power that then other turbines can generate behind, right? So it is a fantastic optimization problem, incredibly it's really an incredibly non-convex problem. This is something we simulate in Ixelles, okay? And it's a simple wind farm. And one of the things we did by using these ideas that I'm happy to talk offline about is how to put these wind farms to optimize and maximize actually power generation, okay? And the uniform placement is not necessarily the most optimal because it depends on the wind direction. And yeah, we end up basically, I mean, this is a very long story short. This is the state of the art. These are like the optimal arrangements and optimal yaw angles, okay? The optimal inclinations, let's say, of your turbines for a wind farm of 10 turbines. And the black line is actually what we found by combining, the scientific machine learning tools with Bayesian optimization. Now, long story short, you see there is a huge difference between the optimum we found and the optimum that is used in the literature. One thing that you don't see immediately, but it becomes apparent by these bars, is that the solid bars is basically the efficiency that is generated by the optimal solution found by our machine learning method, and the dashed kind of line, the green bar, is the efficiency of the single turbine generated by the classical state-of-the-art solution. And bottom line is that on average, except for some turbines, the solid bars are bigger, and in general, the total increase, I can't remember now in percentage, but it was not negligible. It was around on 10% or so. It's in the paper, the correct number. Right, sorry for overrunning. Just the conclusions very quickly. I think the main message is, in my opinion, there is no, in science or fluid mechanics, there is no paradigm shift like sometimes you read in papers. It's just, not just, but it is a fusion of paradigms, physical modeling and machine learning. The two things must go together when we have physics on our side. And that's, I think, a very interesting thing from an academic point of view, but also from practical reasons. So in computer science, you do not want to bias your algorithms. Actually, you hate people doing that. In science, without computer science, just science, where there's physics, you do want to bias your algorithms towards the right direction given by the physics. Then we explain a little bit what predicting chaos means and how we can do that for infinite dimensional systems like PDEs. And I gave you an example without many details, admittedly, on how to tackle realistic and non-convex, incredibly non-convex optimization problems with scientific machine learning. And I wanted just to finish with this slide, which I will leave there, which is, it's not updated, but they are the most important players, and these things were done by students or postdocs, to whom I'm very grateful, and the support from a ERC starting grant and a UKRI and Rolls-Royce, not really. If I talked about real-time Rolls-Royce, but because I didn't talk about real-time, it's just UKRI and ERC who sponsored this research, okay? Anyway, thank you for your patience and attention. I will be glad to answer any questions. Thank you.
So we have time for some questions. False alarm. Okay.
Hi, Luca. Thanks for the talk, and having waited for the conclusion of my talk. So thank you for your patience. As a computer scientist, I have a question that is the following. I really appreciate your point of view because I clearly see the drawbacks of the classical approach in computer science. When you talk to computer scientists, what is the reaction? How, or is there a way to convince them to look at also the other side?
It's a very good question. Because I'm recorded, I need to be diplomatic. So PDEs, partial differential equations, Navier-Stokes, are very scary. It's not cats and dogs. So I would say that we do, I became a computer scientist also a little bit by research, but I think the community is really emerging now at the intersection, and there are many computer scientists doing more turbulence and dynamical systems, and of course there must be some communication, and there is communication. But many papers coming from pure computer science, sometimes of course they tackle some aspects that are more representation theory, more convergence kind of aspects, and perhaps, of course, because of lack of domain knowledge, they look a bit less at kind of the physical properties of the systems that they are inferred. On the other hand, sometimes non-computer scientists tend to sometimes make rookies mistakes in terms of not regularizing properly the neural network, or also the choice of the very neural network sometimes is is not ideal. So I don't have an answer, but I think if for the computer science community, I would like to challenge, but in a good sense, you know, to build a community, to try to tackle turbulence with the various tools that we have available. Because if we can tackle that in a generalizable way and robust way, I think it would be amazing.
Other questions?
Thank you, Luca. So maybe continuing on this discussion, so I think you touched a little bit on this point that when you look at the physical solution of these problems, we have very sparse solutions. We have, in fact, solutions for which we have billions of data points available, but we do not have, you know, the capability of actually representing the state space in terms of the density that we would actually need. Now, the fact that you have some of the data and the physical knowledge of the process, do you see in the future a perspective where we will reach enough knowledge from the combination of those to have predictive models that are really generalizable, interpretable? And
all right, okay, that's a very good question. What interpretability are, I don't know exactly. I think it's a philosophical discussion. Some people will say that something is interpretable if you have an equation for it. Some other people will say if I see structures in it. So I don't know what interpretable means in machine learning, and but I think it's a very important thing to understand why it works. So on interpretable, I don't have a very strong opinion, although I do like understanding why things work. But on the generalizability, that's certainly number one problem. I mean, all these things work, and you can make a little bit generalizable sometimes for some range of parameters. But the point is that, you know, Newton's law work for any possible scenario you can think of in classical physics, which are many scenarios, and in non-relativistic physics, and also non-relativistic physics. So you can imagine how many scenarios. That's generalizability. I'm not sure we will get there with machine learning unless maybe we collect so many data points. But I really think that the combination of the two things certainly improves the generalizability, leaving the freedom also of self-correction. But it is number one thing to do, in my opinion, in the field, is to look at, you know, how to make these things generalizable, for sure. More generalizable.
Are there other questions?
Hello, Luca. Thank you for the very nice talk. A curiosity. So you compare the autoencoder performances against the POD. So of course, linear against non-linear.
Mm-hmm.
But do you envision some more, let's say, informed way of mixing them, like using the autoencoder only to model what is really non-linear, and using the POD to restrict the linear manifold learning
sure.
and no-linear manifold learning?
You can get as creative as you like. I actually presented a fairly straightforward approach, which is compressing everything non-linearly. You can absolutely split your data in principle as, okay, I have a linear subspace and else, you know, and you can leave the else to be learned by the autoencoder. Certainly. I mean, probably it could be also potentially more robust as an approach, potentially, yeah.
Okay, thank you.
So if there are no other questions, I would like to make one question myself. That is, of course, when we speak about merging the world of physics and the world of data, as you were clearly saying, one of the main points is how to enforce constraints in our learning methodologies. Do you think that actually that should be in itself something to research on? Because I think most of the constraints in my field are equality constraints and inequality constraints, which are extremely hard, I find, to map into learning methods. What do you think about that?
Yeah, that's excellent. I didn't really talk too much about that in terms of how we do that. So there are different ways. mainly there are two ways to go about that. One is you constrain something in a soft way. You know, you regularize kind of your network to penalize, you know, anything that violates some sort of constraint, like equation. I call it the soft way. So in the loss function. And the other way, which we worked on, although I didn't really show anything, is to build an architecture that reflects some basic properties that you expect from the physical system. Now, for example, I'll give you an example. I mean, we worked a lot of sound propagation and nonlinear phenomena in acoustics. So we started by saying, well, we know something acoustics, right? I mean, we know that, you know, the solution in a linear limit can be represented as Green's functions, blah, blah, blah. So we started by constructing a neural network that enforces that. And then we left part of the neural network on anything else, let's call it. So that's the hard constraint. When you design something that, you know, fulfills the properties. And in general, yes, there is research to do about that. And that's exactly where the domain knowledge is going also to help the computer science community and vice versa, because you need both quite, you know, intimately connected.
Okay, so I thank you for your answer. I think that the formal, actually I will use the other microphone so that I'm well set in the camera. So with this, we can thank again the speaker as a first thing. I didn't do it for Andrea, but you did it spontaneously, so I feel not too guilty about it. And this said, I think we can close here the formal part of this Thursdays at BrIAS. I say the formal part because you are all invited to stay with us, to drink a glass of water, a cup of coffee, and to keep discussing with us, with the fellows. So I really strongly invite you to stalk the two speakers if you have any curiosity. We are here to exchange ideas, not just to give seminars. So with this, thank you for being here today. Thanks also for the people that are listening to us online. And see you next week, where we will have a series of other two seminars, very interesting, that somehow are a continuation of what we have seen this time. Thank you.